And of course, it's almost lunchtime, so do feel free to go for lunch, because for most of the theoreticians it's not important, the talk. So 90% of the room, including Shankar, has already left, so it's okay. We'll be back to see his lecture later on. So before I go into the topic and I discuss some updates on the graphene interaction with light, I'd like to say a few words on where we are and where sort of we come from. So a few years ago, or when everything started, this is the sort of graphene people can make and sort of, exfoliate and on the substrate, and you have something there. In fact, if you look carefully, maybe you get something even better, and you can see that, in fact, the flakes can be much bigger what they were originally. So they were about 1 or 2 microns in 2004, and now things are sort of much bigger. And then what you can also do nowadays is to take these flakes, clean up everything that is around it, and get some very nice and clean square or rectangular flakes on your substrate. And then you can also take those flakes with a shape that you want and place them wherever you want. So today we saw some examples, but you can essentially design any kind of device or structure and put the flake with a well-defined shape and number of layers, of course, wherever you want, on the top, on the bottom, in the middle, perpendicular. Is extremely easy, and everybody can do it. So this took about 6 years to develop. What I mean, from when we were in 2004 to about 2010, 2012. But, of course, it's interesting for physics, and people here are interested in physics. But then, in 2010, there was also the important breakthrough in Samsung and SKKU. In fact, the breakthrough was mostly technological, because the idea was published a year before by Rod Ruoff and Luigi Colombo of Texas Instrument and Texas University. And you can use copper as a substrate to grow graphene, and there you are. In 2010, you can get 30 inch of graphene continuous production. It was the same time, a few months before, the paper was on CONMAT, then the Nobel Prize. So I don't know, maybe the Nobel Prize in physics was in fact influenced by the fact that this was not just physics. It may be something real, okay? Not, but because if it was just Scotch tape, one wonders if it would have been so quick. Yes, single layer 30-inch continuous product. I believe that there was a press release from Sony or somebody a few months ago about either 100 meters or 1 kilometer of graphene. I forgot the number. But basically, you can make as much as you want nowadays. The progress has been extremely quick, but is more or less on the same time scale as what happened for carbon nanotubes, because, of course, there was papers in 1950s on carbon nanotubes, as there were papers in 1860s on graphene. But let's say when the whole thing started in 1991 with Ijima, in 1996 there was a paper in Sandia National Labs in Science on large-scale growth by CVD of nanotubes. So it takes about 5 to 6 years if the material is good and exciting for engineers to come there and make hundreds of meters. And that's relevant for what I'm going to say in a few slides. And in Europe, there's this company that has just, in fact, there is only one company. There are some small startups, but in terms of large companies selling graphene production system, Einstein has just launched this system here that you can buy, and if it works, you basically put the wafers in, press the button, and it gives you 30 centimeters, 300 millimeters wafers, continuous production. It costs a little bit of money, but okay, this is meant for industries. They have a smaller version called the BM whatever that is cheaper and is meant for universities. So we are sort of getting there somehow. And of course, there's another way of making graphene that is not again such a novel idea, as most of those things are not such a novel ideas. If you go in any graphite mine, and I apologize for taking a Brazilian one, because of course India has a lot of nice graphitic mines, but I've never been in a graphite mine in India. Maybe next time somebody should invite me. But I think they look all the same, no matter where they are. There are some rocks and some mountains, and people take off the rocks, and with different means. And then they chuck everything in some sort of bath with lots of chemical stuff. They destroy all the rocks, and they extract the black stuff, which is the graphite or whatever it is. So in principle, if miners can do this for hundreds of years, or since when graphite is used, maybe you can improve a little bit the system and start from graphite flakes, and then you can get individual, ideally 100% separated flakes in solution. And again, that started in about 2007, 2008, and by 2012, it is nowadays, we can have bottles of graphene at the production. It is about grams per hour, but very soon, maybe in the next year, multi-kilogram per day, and already companies that are planning tons not per day, but probably per year or something in production. And once you have these bottles full of graphene, then you can apply other techniques. This is reflexographic printing. Basically, you go in any newspaper, place where they actually still print newspapers rather than reading on the internet. And they have all these rolls things, and they put some ink, and then they print stuff. So once you have graphene in the solution, you can do the same. This is some example, yet unpublished, but this is a picture. Is a plastic substrate with, of course, graphene written on it, but some of these are RF tags and other devices. So chemical vapor deposition, solution processing, the two main techniques that are emerging for large-scale production of graphene. And plus, when it comes to Scotch tape, we're now in a situation where we can do whatever we like. So it's a sort of big progress. And so what is the challenge here? The challenge here, we can stay always in the lab. And I mean, this is important for everybody, including people who study the fractions in fractional quantum effect. The funding will stay there, and the interest will be there in graphene if we can manage to transition to the factory floor rather than staying only in the lab, or the two working together. And of course, the three main areas that have been identified at the moment are printed electronics, energy. If you get the joke on the supercapacitor, most people, they don't. And then, so the body area networks and interaction within devices and so on. And in the meantime, we need to deliver an impact, have know-how and capabilities, and developing new leaders in this field. And to do all of this in Europe, we've been working for the past 2.5 years. Of course, Andergheim and Kostya and everybody was involved, also Fert and von Klitzing. All the Europeans would care about the system. For the past 2.5 years, we have been lobbying the European Commission to give us some cash. And last week, or the 11th of December, we were in Brussels, me, Andergheim, and somebody else, and we had the final hearing with the representatives. And on the 28th of January 2013, they will announce the decision on the funding. We are speaking about 1 billion euros funding, so it's a large amount of money for the next 10 years. So 100 million euros funding per year for the next 10 years. That is relevant, I think, for everybody, including for India, because if we fail, the message will come that graphene is essentially dead, and you can better change field of research. If we don't fail, and we will know it in a few weeks' time, this will boost graphene research and graphene industry for the next 10 years in Europe, with knock-on effects, of course, in Asia, US, Japan, and everywhere else. So even though the money comes to us, it's important for everybody due to the such prominence of this. Okay, let's finish with the politics, and let's go to some talks. Of course, there is this guy here that most people should know, and he is very important, and Raman is very important in graphene because, if Raman was not there, of course, you can do quantum Hall effect measurements and know if you have 1 layer or 2 layers or whatever, but no industry will ever even think about doing that. And after, the other problem is not really doing the quantum Hall effect measurements, but is that after you've done them, what do you do with the sample? You throw them away, okay? So you need a system to identify the sample, and Raman spectroscopy is what tells you what you are. So I'm not going to do a sort of a summary of it. I just want to show some more recent progress in the past 2 years in this field, and then move forward. So, in fact, the Raman fundamental selection rule is not even a selection rule because it's almost equal to 0, is that the phonon exchange is almost equal to 0, wave vector almost equal to 0. So it's not really much difficult to understand, it's just energy conservation. But however, when you have more than one phonon, it is the sum that has to be almost equal to 0. So it means the overtones are almost are always Raman active. And so it's not really surprising at all that we have an overtone here, which is the second order of the D peak. The D peak is not seen at all in the Raman spectrum because it's forbidden. It doesn't satisfy the selection rule. But the sum of the Q plus minus Q is 0, so you see the 2D peak. So it's actually, there's no big science there. It's actually very simple science. What is a bit strange, and it took quite a few to understand, is why the intensity of the peak is so large. On the other hand, if it's so large, it's good because it's easy to see and characterize the samples. We thought for many years that the G peak was very easy because the G peak is the Q equal to 0, so it's what is Raman active normally, and there should be no science, no particular science in it. And it's the standard peak. It's called the G peak because when you take a piece of graphite, you stick it in a Raman spectrometer, press a button, you see one peak, and it's graphite, you call it G, okay? That's the whole story of the G peak. No particular science in it. And it's some sort of mode where there are sp2 rings moving one with respect to the where there are carbon atoms moving one with respect to the others in a ring. In fact, you have the G peak in any carbon material as far as there are sp2 bonds, because you don't really need a ring to have two carbon atoms moving one with respect to the other. So even if you take diamond with a little bit of inclusions of whatever, you still see the peak. And so, you arrive, there's excitation, there's emission of the phonon, and there's a scattered event. It obeys the fundamental selection rule. There's no disorder. Well, in the ideal case, with no disorder. So everything seems like undergraduate or even high school physics, okay? And there is one virtual state. However, the intensity of a Raman process is not so easy, at least to calculate. It is easy to write the formulas, but in practice, up to now, there have been probably 1 or 2 Raman calculations in graphene or graphite, and most of them were wrong. Not because the formula is particularly difficult, it's quite sort of straightforward, but most of the terms are not really well known, and so when you do the calculations, you don't know where all the resonances are, and so on and so forth. So, but even if it's not such a difficult formula, still most people don't want to do this calculation. So what Raman people tend to do, they look at it, they go and look at the denominator, they see which terms are sort of the smallest, so this will be the biggest contribution, they throw everything else away, and we don't consider the sum over all possible resonant and non-resonant processes. So we only end up with one matrix element, very simple one. But of course this is wrong, and if you did want to do the calculation properly, you would have quantum interference effects, and quite surprisingly, nobody considered this until 1 or 2 years ago in the case of Raman spectroscopy. And especially nobody considered in the case of the G peak, which seemed to be a very simple and straightforward situation. In fact, there was a paper in 2004 by Thomson and colleagues where they actually suggested you should look at quantum interference, but they themselves did not look at it and they didn't care, and nobody else cared to read the paper, or at least that part, after 2004. While the first decent paper on the subject, purely theoretical, is in New Journal of Physics of Dennis Basco in 2009. So after 2009, people started thinking a little bit more about this. So in fact, in the G peak, it's not as simple as I showed before, but all these processes in a pictorial way are all possible. And in principle, we think, okay, this one is the sort of most resonant one, so these two will sort of go to 0, but that's not really the case. You need to do the sum and see exactly what goes on. But what is sort of intuitive is that if I do change the doping, for example, I can kill some of the processes, and for example, if this one and this one were canceling out for some reason that we don't really know, in this sample, they will not cancel out anymore. So there is a way of tuning the weight of each of the matrix element in the sum, and doping is the easy way to do it. In fact, there was in 2010 an example where they, from the group of Dresselhaus, where they calculated the Raman, they sort of not calculated, they measured the Raman intensity, and they saw quite strangely that for a very high potential, this is the electrolyte doping, there was a very large increase in intensity, and that is quite unknown. In fact, the same experiment was repeated in Berkeley and published in Nature in 2011, where again they looked at the G-peak intensity as a function of doping, and at a certain doping, the G-peak was shooting up very much, and the situation is exactly what I described. It can explain by the fact that at a certain doping, for some reason at intrinsic sample, the processes, the type 1 and type 2, they cancel out, but actually when you cancel one of the processes, they don't cancel out anymore, so the intensity is much bigger what you have only in the resonant case. So all the other terms that we throw away are actually important. The problem being, experimentally, that you need quite a lot of Fermi level shift, like 0.8. You need to have basically the laser energy to be of the same order of magnitude. The laser energy divided 2 has to be of the same order of magnitude of the Fermi level, which means since the lasers that people use in Raman are about 2 eV, you need about 1 eV doping, and doping a sample to 1 eV is not that simple. Actually, if you use a gate, it's impossible, so you need to do something else. And then, of course, we have the 2 and 2D peaks, and in this case, this is the simple process, and there is a process where all the intermediate states are resonant, and we could, in principle, have a similar situation where all the other states actually contribute. And in fact, what it turns out that in this case, what is the full resonance approximation, so only considering the most resonant of the terms, is actually good. So there's no surprise there, unlike what happened in the G-peak, even though the full resonance approximation that has been used for many years, well, not for many years, since 2008, is actually not strictly speaking correct. So the intensity of the Raman spectrum depends on the electron-phonon coupling, but also the electron-electron interaction and the radiative rate, which is quite small. And so if we could modulate the intensity, as I mentioned before, if we can change, for example, the electron-electron interaction. And this was a very important work that was done here at the Indian Institute of Science in collaboration with us, and where we together, or at least Ajay first, and we sort of got the idea from them. There was this problem that it was not possible to gate the sample with normal gating, otherwise you will blow up the sample. And so you could use the polymer electrolyte to induce very large dopings, because there's the so-called debye layer that is very small, the capacitance becomes very, very big. So instead of using 6,000 volts, you can use 2 volts and get the same result. You get large doping effects without blowing up the sample. Simple idea, very important, a lot of follow-up, including for all the experiments for basic physics and so on. So this is all work, so you could do that, but with a voltage that is extremely small. And you can get the change in Raman intensity and so on. And that was explained, as I showed before, in that in that work, that you change the electron-electron interaction by changing the doping level, and so the intensity of the 2D peak is changing with respect to the one of the G peak. There is however, even polymer electrolyte, as good as it is, you cannot really get 1 eV, 1.5 eV of doping, because it's simply not, unless, if you do try, what happens is that you damage the sample. There are some interactions between the polymer and the graphene. So the next step to get very high doping is to do intercalation, and for example, iron chloride in this case, and intercalation compounds have been known for many, many years. So if you put the intercurrent in the middle, you can decouple the individual layers as well as getting a very high doping level. So this is a undoped sample, for example, a bilayer. Once you put the intercurrent, the 2D peak starts behaving as the case of a monolayer, because the intercurrent is shifting one layer from the other, and so the bands are not interacting anymore, or not so strongly interacting, and so essentially they start behaving as individual monolayers. And if you're not very careful, or if you leave it in air for a large period of time, there is some desorption of the intercurrent, and you can get, for example, the splitting of the G peak, which is known when you have a non-uniform doping in the sample. Okay, this is some sort of background here. So before we looked at what happens for a given sample, for a given excitation energy, when we do change the doping level with this debye layer and so on. But now what happens when we have a given doping level, because we have an intercurrent, so we can only dope so much, but we do change the excitation energy. And so what we see is the intensity of the 2D peak can be very large, and one excitation energy can be completely zero and another excitation energy, but it's exactly the same sample. I'm not changing the sample, I'm changing the excitation energy. But actually, it's not so difficult to understand. It's a very easy situation. It's the simplest situation with respect to the one of the G peak. If I dope enough, there are, for Pauli blocking blocks, the transition, get the most resonant transition that gives rise to the 2D peak. And since the non-resonance transition, as I mentioned before, they contribute very little. In fact, this is experimental. Or if we didn't know if they did contribute very little, we can now experimentally prove that they do contribute very little because you don't see anything, okay? So once you kill the most resonant transition by changing the excitation energy, in this case, not by changing the doping, the intensity of the 2D peak can be completely suppressed. Okay, so there's other work going on there, but I don't have time to discuss more details, but people now have access to like a large doping and other funny things can be studied. I just want to go back to the beginning again. If you look at graphite and graphene, there's this E to G mode. So let's forget about the second order peak. Let's stick to the Q equal to 0 that I mentioned before is the Raman allowed phonon at the gamma point of the Brillouin zone. And as I mentioned before, there's the G peak, and that's sort of the usual one. The reality is that there's more than one phonon that are allowed at Q equal to 0, but most people only study one of them. So there are different possible phonons, and some of them are Raman active and some aren't. And when you go to graphite, for example, the E to G mode splits in an infrared active and the Raman active one, and the Raman active one is the famous G peak, and there are some works to study the infrared activity. Then we have the B2G, which is not Raman active, and when it splits, when it goes to graphite, it splits in infrared active in another silent mode. And then we have this layer braiding mode that has been studied also here theoretically and experimentally. And then what I want to focus upon now is this E1U mode that does exist in graphite as a Raman mode, active mode at about 40 centimeters minus 1. But in graphene, of course, it's a single layer, is U, so it means it's not Raman active, and is not seen. So when we look at the evolution of the Raman spectrum with a number of layers, the reason why the 2D peak is changing in shape is because the band structure is changing in shape. So it's not because it is a phonon that actually cares about the number of layers. The D peak is a completely in-plane phonon, and in first approximation doesn't care if it's 1 layer, 2 million layers, or 20 layers. What does change, it is the band structure, and in the Raman process, you're probing the change in the band structure with the Raman scattering experiment, and so that is why you can distinguish 1 layer from 2, and that is why Raman is so interesting, because at least otherwise it would be sort of only for boring people like me. It's interesting also for people who care about electrons, because the electrons are crucial in the Raman process, as I mentioned before. However, there are some this particular phonon is due to the relative motion of 2 planes. So this phonon actually cares if there is 1 layer, 2 layers, or 20 layers, and is a phonon that directly is probing the number of layers in the sample. The problem is that the frequency is very small, 42 centimeters minus 1. And okay, maybe this is boring for people who don't do Raman, but for people who do Raman or Brillouin spectroscopy, they know that with the traditional Raman instruments, especially with the one that people buy now industrially, have notch filters and so on, so it's basically impossible to get to low frequency. So it's a little bit of a challenge. But even if you have a non-traditional Raman system, like there are many, a non-modern Raman system, but a sort of one made for physicists, and there are many here, it's still a bit challenging, because when you do the Raman measurements, this is a piece of graphite, you expect to see this peak and you see nothing. You see actually a big background. So this big background actually comes from the silicon, and if you do remove the background of the silicon by doing polarized Raman measurements, you can start see these peaks here. So we call this the C peak, because it's related to the interlayer coupling. So it turns out that you can suppress this electronic scattering from the silicon, for the silicon dopants, by changing the polarization. And so if you do polarized Raman measurements in graphite, you can start seeing it.
Sorry, how many layers are there?
this one is a bulk piece of this is 3 layers, but it could be bulk, whatever. I mean, this 3Lg means 3 layers of graphite. If it was 1 layer, you would not be able to see it.
Silicon is unintermittent.
No, silicon is the substrate, because usually you put graphene on silicon because you can see it with your own eyes because of the silicon oxide interference. Of course, if you want to get rid of the silicon, what you can do is to drill holes in the silicon substrate. You put the graphene on the top of the hole, then you don't have the silicon anymore, and then the measurements become much easier. And as you see here, this is the bulk, 11 layers, 2 layers. The C peak appears very nicely, and you can study it. So it does exist, and then you can do the measurements, and you can see that the position of this peak actually changes with the number of layers, as you would expect, from 2 to 8 layers. And you can also fit all the data, and I want to show the fit here. This is the G peak position with some scatter, and that's the C peak position, and the scale is essentially the same. So there are about 16 centimeters minus 1 between here and there, and about 16 between here and there. And there is a massive change in the C peak, while the G peak doesn't change at all with the number of layers. Yet again, because the C peak fundamentally is totally in plane and doesn't care about the layer number. So in this way, we can actually monitor directly the change of peak position with the number of layers. And the interpretation of this behavior is actually quite simple. So this is a relative motion of 2 planes, and you can model it as a ball and stick model with some spring constant in it. And there is a very, very simple formula that you can extract by hand that gives you the frequencies as a function of the number of layers. And there's also giving you the displacement. And the only 2 unknown is that the mass per unit area of graphene, which is not really unknown, and the force constants per unit area, which may or may not be unknown, so the interaction between the planes. So if you actually go for n equal to infinity, that is graphite, the formula becomes even simpler. So the frequency is 2 square root of alpha divided mu. Omega is known, mu is known. You can extract directly alpha from a very simple Raman measurement. And in fact, if you use that very, very simple formula, that's the blue line with nothing else, you can fit all the data, the experimental data, in a sort of very, very nice way. So we can get this interlayer coupling constant, which is 12.8 10 to the 18 Newton per meter cube. And this is directly related to the shear modulus of the sample, and which is about 4.35 gigapascal.
Is it obvious that the interlayer coupling is the same in 2 layers as it is in 3 layers as it is in 4?
Yes. To a first approximation, that's...
First approximation, yes.
Yes. But of course, if you want to, then you can argue that there's a slight difference between that and that, but plus or minus X% is the same. It doesn't change as a function of the number of layers, and that's the key point there. And of course, we can also measure apart that we can measure it directly from the experiments, and if there are changes, they are very minor. So that's the first message. The other thing is when we look at the detail of this peak. So, for example, the full width. So the peak can decay by phonon absorption or by electron-phonon coupling. And in fact, what we see is that this peak has a final line shape, and the energy here is quite small, of the order of milli-electron volts. So we argue that we have actually a Raman peak that is sensitive to electronic transition at very low energy, close to the Dirac point, while the G peak and so on is about 200 milli-electron volts, so it's very far from there. So we think there is a Fano interference there between this low energy electronic transition and this Raman mode. And of course, we discussed about the 2-layer and the bulk. The reality is that there are, as a function of number of layers, there are many possible combinations. And what we have seen so far is only the higher frequency one. Of course, the lower you go in frequency, for example, 10 centimeters minus 1, the more difficult becomes experimentally. And the electron-phonon coupling, thus the Raman intensity of this mode, is very small anyway, so it's quite challenging to measure them. In fact, nowadays the trend is to go beyond graphene, and if you go back to the first paper of Kostya on the subject, the title was not graphene, but was 2-dimensional atomic crystals. So already in that paper there was graphene, but there was lots of other materials that were already exfoliated, And there are lots of materials that are layered, and you can extract individual layers out of them. And so this opens two fields of research. The first one is to do basically what you did with graphite. For example, in MOS2, if you take a monolayer, is a direct bandgap semiconductor. If you take a bulk, is it direct bandgap? If you change the number of layers, all the electrons change and everything else. So there's quite interesting physics to be done there. But the second point is what you can do now, since we can manipulate all these layers individually, is to take all these layered materials and construct artificially, initially by hand, some new material that doesn't exist in nature, of course, because there's no mine where you can extract this, but that has all sorts of different layers of different materials arranged. And this is the latest frontier. In 2012, there are already a few papers on that. At the moment, this can only be done by hand, so it takes a student or a postdoc several weeks to create one of these materials. But of course, what I said before, there are already people looking at how to grow graphene on BN, how to do multilayers by CVD, and by solution processing. So it will take time, but in terms of physics, you can think all sorts of things you can do now by putting together these materials artificially. Yes? As I said, there are already some initial results published, mostly in 11, 12, 13, so very recently on these new materials. And in fact, in principle, we have layer-by-layer material engineering with almost infinite possibilities. The limit is how either lucky or clever you are in finding out which is the combination that gives you a good result or something exciting. But as I said before, we can already do, since 2011, the exfoliation in liquid and get all sorts of layered material liquidly exfoliated. And of course, also in these materials, you have a shear mode that has mostly not been studied, and this is an example in the bulk of BN, graphite, bismuth selenide, bismuth telluride. And if we want to go more in detail, in the case of MOS2, and I don't want to bore you to death, but essentially all these modes are now accessible, and there are two main categories of mode. One is the C mode, so is the shear, and the other one is called the layer breadthing mode, is the planes moving one with respect to the other like this. The one is the shear, the C mode, and the other one is this mode, okay? So these two modes are very low frequencies. They've all been studied, and okay, if you do Raman, it's interesting. If you don't, they're not, but whatever. There's lots of interesting stuff there. You can identify them and model them. In fact, there are lots of families, and this can be modeled in first approximation. DCM is essentially ball and sticks, and you reproduce very, very nicely most of the experimental results with little variation. So now all the story is sort of taken on, and the reason why it's become very simple to do the measurement is that a company called Bragg-Great has developed a set of filters that can be retrofitted to the most modern Raman spectrometer systems, and so you can do, since about 1 year, you can do these measurements with high intensity and you don't need to use an old triple spectrometer in addictive mode and so on and so forth. Well, in fact, being here, people should be excited about the Raman details, but maybe not. Okay, so, well, maybe it's like, the sons, they have to kill the fathers, and so we that we're not Indians have to love Raman stuff. And so let me go spend the last 5 to 10 minutes in other stuff with light, graphene optoelectronics. So in optoelectronics, we deal with light detection, and the high carrier mobility for both electron and holes makes graphene ideal for fast photodetectors. Light emission, the tunable bilayer bandgap makes graphene ideal for tunable light emitters, and light modulation. And the optical properties of graphene can be modulated by fields, and so we can get electro-optical modulators. So graphene is the only material existing in the world where whatever light you're using, you always create electron pair. You think it's kind of obvious, maybe it's very simple, but if you think about the actual other materials, they don't exist. And so this opens up a lot of possibilities that are just unthinkable with any other material. Lasers working in any wavelength, detectors working in any wavelength, solar cells that use all the spectrum of solar light and not just one wavelength.
That's only true for undoped.
That's only for undoped graphene, but when we speak about light, we don't care about the doping of the paddles and so on. because we are speaking about 5 millielectron volts, maybe 300 millielectron volts, the sun, and everything else is much higher. There is only one frequency where the problem is where there is a problem, is terahertz, and very low frequency. That's very useful for airport. I see that now there's full scanners everywhere, even in the hotels. So, okay, that is being sorted out as well in 2012, but I will not really have time to go there. So we can have ultra-fast conversion of photons and plasmons in current and voltages. And the other sort of new stuff in 2012 is plasmons in graphene. We discussed about plasmons, but there are also plasmons, and those happen at high carrier density, and they are very interesting, but is a very new sort of field, and I'm not going too much into the details about that. So the idea is to have highly integrated graphene photonics that are compatible with standard CMOS processing, but of course, if you want a flexible device, then graphene is the only opportunity. And let me, time is up. I wanted to show a few other slides, but let me skip them on something on Raman. I just want to show you briefly a summary of what is the situation now with a few recent results. So graphene absorbs 2.3% of the light, which is good and bad. You know, it's good because it's only a monolayer, so it's huge absorption. But if you want to do a detector, it means most of the light goes through. If you want to do a solar cell, most of the light goes through. So you need to increase the interaction between light and graphene in order to exploit these properties. So there have been different options. One is the combination of graphene with plasmonic nanostructures, such as metallic nanostructures. If you have a metallic nanostructure, the local electric field is increased. Since graphene absorbs everything at 2.3%, if the electric field is hugely increased, the absorption of light is hugely increased. And in 2011, we have shown with Manchester this combination of gold quantum dots with graphene, and the initial results showed an increase of 20 times in the responsivity of the material. The other option is to combine graphene with semiconducting nanoparticles. In this case, those do the light absorption, and they create electron pairs, and then graphene is helping extract them from the sample. And again, there are pretty amazing results that were produced in 2012, where responsivity is up to, in fact, now is about 10 to the 9 ampere per watt have been achieved. 10 to the 9 ampere per watt is basically close to single photon detection, so a new field of research is being opened there as well. The third example, I have 5 examples, so very short. It will be, instead of interacting with graphene perpendicularly, why don't we interact with graphene along the graphene plane? And there are few experiments ongoing now in order to have the interaction between light in a waveguide along the graphene plane that will allow 100% absorption and generation of photocurrent. I don't have any results for this one. You know, of course, about microcavities and cavity QED and so on. So in order to start this study, you need to take the graphene and include it in a microcavity, which is what we have done, again, this year with IBM. You take the graphene, you include it in a microcavity, then there's the Purcell effect, all the nice things that can happen when you confine light in a cavity. To do that takes some time, but as I mentioned at the beginning of the talk, everything can be done now. So you take a silicon nitride membrane, which is semi-transparent. You put graphene on the top. You also put source and drain contacts. Then you grow by ALD some aluminum oxide. And then you have to deposit the mirrors, the semi-transparent mirrors, on the top and at the bottom. And then you have your cavity. And once you have the cavity, for example, designed by the green, it looks green, and so on and so forth. Again, cutting a long story short, you have an enhancement of interaction between light and graphene when you are in resonance with the cavity, as you would expect. And the other thing you can do a cavity-controlled thermal radiation. So a graphene in the space, in the free space, is emitting sort of a Boltzmann emission. Why, if you are inside a black body emission, if you are inside a microcavity, you are confined in the emission that you can have. Again, let's cut a long story short. Outside the cavity is a black body radiation, so there are these sort of lines, nothing special. This is a different cavity design in 925. When you are inside the cavity, the emission is peaked around the cavity resonance. And to answer the question of Arindam before, what happens if we go to the terahertz? We have the doping. Doping is impossible to get rid of at that stage, so Pauli blocking will always block the interaction of light. You will not have a generation of electron-hole pairs, so in principle, graphene will not be useful in the terahertz range. However, if you have an oscillating terahertz field between gate and source, you can generate a photovoltage based on this sort of simple relationship. Is the old relationship by Diakonov and many other people. I mean, it's a sort of well-known effect. You can essentially interact with the plasmon in the graphene, and that will generate a modulation of the charge of the channel, and that gives you the photovoltage. Again, cutting a story short, we have created a transistor, an FET with graphene, but we have coupled it with light via an antenna. This is a log normal antenna. A log normal antenna can be designed in order to be resonant at different frequency. So the length of these little spikes defines what frequency the antenna works with. And that's the actual real device. So that's the graphene you cannot see in the middle. That's the antenna. And these antennas are designed to interact with light in the terahertz spectrum. The graphene is in the middle, and there's a source drain at the top gate.
Is that the same device that you showed?
Yeah, it's the same. You can probably see the little blue stuff here, and then a zoom of that part is here. That's what is in the middle. The antenna is quite large, and the graphene is in the middle. Well, it's quite large. It's large, but it's not like 6 meters. I mean, we're speaking about hundreds of microns, okay?
Are these on silicon oxide substrate?
Yes, this is on silicon oxide. Simple graphene, silicon oxide, a simple antenna design. You can download the software from the internet to design. This is what people that fix the antenna on your roof can. It looks like the one in the roof, but it's like this instead of like that. So it's basically 200 years old technology. Just make it small, and we finish. And it works. So that's a detection of a leaf with this terahertz device. It's about 6 centimeters times 9 centimeters, and you can see the leaf veins inside, okay? But if we want to use it for security, we didn't have bombs to check, but we had these are boxes for coffee machine. That you put this thing in the coffee machine, you press the button, and the coffee comes out, and you buy them in these cardboard boxes. So if you want to look inside the box and see if there is our capsule for our coffee machine, we can just open the cardboard boxes and look inside. Or you can spend 2 years to design a graphene-based Terahertz detector, so you can look inside without opening the box. So if you do spend 2 years, maybe the coffee goes bad in the meantime, I don't know. But you build the device, and then you look inside. You can see that these are your coffee capsules, and here some sort of terrorist has put some piece of metal or something, and it's not good. But being experimentalist, you need to prove that this is the truth, so you have to sacrifice eventually your card box and open it. And if you do actually open it, you can see your coffee capsules, and yes, there was a piece of metal there. So this is only 1 pixel, 1 detector, but since it takes nothing to get the image, you can scale. This is macroscopic, of course, you can easily do the scanning. And I conclude here, by thanking everybody, and in particular the work that was done here at the IIS, and Joyce Group and everybody else. Okay, thank you very much for your attention.
There is time for a few short questions. Arindam, you had a question?
Yeah.
Thanks. What's the resolution of imaging that you can now do with graphene terahertz detectors, for example?
Well, that is defined by the size of the graphene device, so that was order microns. But terahertz detectors are usually never utilized for nanoscopy, but they're used for macroscopy, because you have big objects that you want to check, or entire bodies of people. So we don't really bother with the resolution.
Okay.
But of course, the wavelength is whatever it is, and so you are limited by that, as in everything.
Does it matter if you use single layer, bilayer graphene?
No, it does change, and of course, with bilayer graphene, we got, to be honest, the image was done with the bilayer graphene because we get much better results. If I have to be, but still graphene is, it's bilayer, monolayer. No, it's graphene, but yeah, if you increase the number of layers, it's better. If you have too many layers, then they don't work anymore because they absorb all the light. So 2 layers seems to be better than 1.
I have a short question. You said you put some nanocrystals and the sensitivity to detect light increases.
Yes.
So how does graphene help?
So there are 2 options. One, if you take a gold particle or metal nanoparticle, you put on the graphene, then you know that if the particle is in resonance with the light, the local electric field goes to e to the 4th, and essentially graphene absorbs everything. And so that's the first trick. Second trick, you take a nanocrystal which is semiconducting, like lead sulfide or something like that, and in this case, you have to be in resonance with the crystal. These crystals have a huge interaction with light, so they generate a lot of electron-hole pairs, but graphene can sweep them away. In fact, graphene is so good that graphene is suppressing photoluminescence when you put these nanocrystals on the top, because it sucks out all the charge carriers. So in this way, you get the nanocrystal to create electron-hole pairs, and graphene to take them out very quickly. And in fact, the responsivity, as I showed, is huge. The responsivity in graphene, of course, once you generate the electron-hole pair, those 2 guys, they want to recombine, they don't want to get out. So in order to get them out, you need a potential. So the easiest detector, you take a piece of metal with a graphene, there's a built-in protection, there's a different Work function, and it creates it creates a potential at the interface that destroys the electron-hole pair, or that takes out the electrons and the holes from the other side. But in that case, the responsivity of graphene is about 1 milliamp per watt. Then if you do these metal nanoparticles, we can get up to 20 or 50 milliamp per watt. If you do a microcavity, you can get up to maybe 100 milliamp per watt. But if you go with a semiconducting nanocrystal, it's up to 10 to the 9 or 10 to the 12 amps per watt, which is much better than the standard silicon detectors and so on that is in technology. Of course, there is a trick in everything, because in one side you lose the tunability. The semiconducting nanocrystals are very slow. So in principle, graphene is ultra fast, 10 femtoseconds. I don't have time to show the ultra fast dynamics, because very recently we have started with 7 femtosecond resolution lasers, the electron-electron interactions, the evolution of a population of hot electrons in graphene while it's spreading out. But you lose that if you use another material that is very slow. So everything you have to give something, but this is all these fronts are very new, so all of them are continuing.
There are no more questions. Thank you very much.
Thank you.
So here is a small memento from the organizers.
Thank you very much.